Hi, hello, and welcome. This is Greg Jacobs. I teach at Woodbury Forest School, a boarding school for boys in Central Virginia, and all my students are gone, so I've got you all watching today. Thank you for tuning in. I'm sure you know that the AP Physics exams will happen. We just don't know what format. We don't know what dates. That stuff is going to be announced on April 3rd, I promise. For now, we're working on building a culture of physics. We're working on learning physics because then the format of the exam won't matter. We are working on meeting other people who are learning physics with us and talking to them and sharing our problems with them, not doing their homework, but sharing our ideas. If you'd like to participate in this community today, at Jacobs Physics, you can get on there at the end of the show today. I will take some questions and try to talk to y'all a little bit. Let me show you what we're doing today. And the doc cam froze. We'll be right there in a moment. Let's try that. Lesson overview. We're going to start with the review from yesterday, Josh's question. Then we're going to talk about 5 ways to measure force in the laboratory. Today's lesson focuses on experiment. I know you know about torque and equilibrium now because Josh talked about it yesterday, but we are going to talk about how we measure torque and equilibrium, how we can linearize a graph to find an unknown value. That's good lab stuff. If you'd like to join the conversation, at Jacobs Physics on Twitter. Here is Josh's problem from yesterday. We want to use the concept of torque and explain why a second student needs to apply an additional tension to put the meter stick in equilibrium. Well, if we consider, let's go live here. If we consider the pivot to be this left-hand side where one student is pulling up with some tension, whoop, then we know that the meter stick itself has a weight, and that weight acts at the center of mass. So that produces a torque this direction. Whoop. In order to put this meter stick in equilibrium, we have to balance the clockwise and counterclockwise torques. That means I have to pull up, and that will cause a different kind of torque, and that will put the thing in equilibrium. So what is the value of T2 in terms of mg in this particular problem? Well, there we can do some mathematics. We know that torque is force times the lever arm, the distance from the fulcrum. Let's consider that to be the fulcrum for now. And we know that the torque provided by mg is equal to the force, mg, times the distance from the fulcrum, the lever arm, which is in this case, L/2. That's the torque that acts this direction. I never know whether that's clockwise or counterclockwise. It's just that direction. That's equal to the torque in this direction, which is equal to T2 times the entire length of the meter stick, L. I call that L up there. All right, we want to know what T2 is. Solve for T2. There we go. T2 is half of mg. Number 3, describe any changes to the required T2 as student B gradually moves closer to the center of the meter stick. We're going to do something like this experimentally today, but let me just show you. He's pulling up toward the edge here, and we want to know, what does he have to do? What has to happen if he pulls closer to the edge? Well, we know that the torques still have to balance. We still have to have an equal amount of clockwise and counterclockwise torques. The weight of the meter stick doesn't change. The distance of the weight of the meter stick from the pivot point doesn't change. So that doesn't change. The distance from T2 to the pivot point does change. That goes down. This is an inverse relationship then. T2 has to go up to maintain the same mg/L/2. So the tension that T2 applies is bigger as the student gets closer to the center. And finally, what happens to T1 as student B approaches the center of the meter stick? When T2 is at the center of the meter stick, then we can say that the torques provided by mg has to be equal to the torque provided by T2, but that would also be L over 2. And so that would mean T2 is equal to mg. As the person approaches the center of the meter stick, T2 will approach mg. That wasn't the question. The question was about T1. Well, let's look at not torque equilibrium, but force equilibrium. If the student is pulling up with a force T2 and the meter stick has a weight mg and T2 is equal to mg, well, that's already in equilibrium. That means that T1 has to be 0 in order to maintain force equilibrium. That's an excellent question. Thank you, Josh. If you'd like to tweet at us at Jacobs Physics, I will be glad to answer some of those questions about that problem, but that's not what I want to talk about today. I want to talk about experiments. I want to talk specifically about 5 ways to measure force in the laboratory. The question that we would be asked on an AP exam might be the mathematical question we just answered. Those are great questions about describe, use words, explain. But we also could be asked, how would we measure the necessary force to maintain equilibrium? So here is a meter stick pivoted at the center. I'm going to hang 200 grams of mass, that is a weight of 2 newtons, here at the 10 centimeter mark. And my first question of the day is going to be, how much force do I have to apply at the 20 centimeter mark? 40 centimeters here, 40 centimeters from the pivot to here, and then 20 centimeters from the pivot to here. And I want to know, and this is 100 grams, 1 newton here. And I want to know, how much force do I have to apply here to keep equilibrium? 1 newton there, how much force here, half the distance. You all can make that calculation. That's not the point. The point is, I want to know, how do I measure that? Well, I can come up with 5 different ways to make that measurement. The first way is, I can just hang some weight here. Do the same thing over here. And see if that balances. And if it doesn't balance, like, it didn't balance here, add some more weight. Whoop. And try to do it with 2 hands because 1 hand doesn't work. Oh, look at that. Yeah, now it balances. There we go. Now the thing balances. No, it doesn't. Thought it balanced. I think I have not enough weight on there. Try that one. Now you're getting a real flavor for my class. There we go. There it balanced. And this here happens to be 2 newtons of weight, as you might have predicted if you were given the numerical calculation. Okay, but there are 1,000 different ways to measure that force. I could use a spring scale. A spring scale is like the scale you would find in the grocery store to measure the weight of your tomatoes. I can use this to pull downward or to pull upward. I'm going to pull downward in this case. I have to 0 this scale downward. I doubt you can see this, but I've got this on 0 now. Try to balance this again. Balance at the center. Put this through the hole in the string. And again, we're trying to do it one-handed. There we go. Pull down, and you can't read it, but I can. And you know what? Once I put it on the 50 centimeter mark, it reads 2 newtons, as you would expect. All right, how else could we measure a force? Well, force is measured by a scale. What about this scale? That's a platform scale. It measures a normal force, but that's not going to work because, first of all, it doesn't work upside down. That's what happens if you try to put it upside down. And second of all, it doesn't localize the force like these other things do. So that's not going to work for us. Well, what else can we use? We can use a force probe. This is what Josh used yesterday. It's a vernier force probe. I'm going to connect it to my iPad, put it on here, and since I want to pull down, I'm going to 0 this upside down. Booga, 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 booga. Come on. Come on. There it goes. There it goes. So I've got a hook on the end of this. I want to hold it upside down and tell this thing to 0. Now I'm going to pull down at the location I've been using. You can't see me, but I can see you. I'm taking the spring scale off and I'm replacing that with the force probe. And as I did before, I am struggling to get this force probe through the hole in the string, but I got it now. I'm 20 centimeters from the edge and I'm pulling down and it's in the neighborhood of 2 newtons. You probably can't see that because the document camera froze, but I will show it one more time. One more time, if we can get it to work. And my doc camera is giving me trouble. So I'm going to go away from it right now. Oh, wait, here we go. I'm going to pull down and I'm going to go away from the document camera because it's giving me trouble. All right, here's what I'm going to do next. I'm going to put this out here so you can see it. Don't worry, I was planning on doing this anyway. What you are not going to be able to see so well is what I'm doing next. I might go over to the camera to show you. I want to do this one more way. A spring scale can't only pull. A spring scale can also push. So I'm going to hold this up here and I'm going to push down. Josh did this yesterday, but I have a neat little tool here that lets me, try one more time. It lets me unscrew from the force probe and put in this thing that pushes. Now I can push down with the force probe. So I've got 5 different ways, 6 different ways to measure force in the lab. And I'm going to do that in just a moment. All right, why am I going through all this? Because an AP question that is posed in an experimental setting is not going to be like the laboratory exercises you do in your class. It's not going to say step 1 through step 12. Follow these steps and get the teacher's right answer. The problem is going to say, explain how you would measure this using equipment that is commonly available in a high school classroom. Well, I've just shown you 5 different ways to measure forces in a high school classroom. Do you have all this equipment? Do you have one of these force probes? Maybe, maybe not. It doesn't matter because now you know how one works. If you have spring scales, if you have hanging masses, I mean, these things have been around since the 1920s. You've got something like this and you know what equipment is typically available. So all you got to tell me is what instrument you're using and how are you using it. Don't tell me that I'm using a balance scale like this or an electronic balance to measure the force that is being applied on this meter stick. Let's do an experimental question. Here we go. And come on, little buddy. There it is. That's the experimental question that I want us to do. We're going to set up the meter stick. I'm going to call the hanging weight F1. It's going to be pulling down, just like it was before, except I'm going to make a new amount of mass on that hanging thing. And then on the right-hand side, I'm going to push down with my force probe. And I'm going to vary this distance from the fulcrum. And I want to use the slope of a best fit line to determine experimentally the value of F1. All right, you can certainly pause the video there if you want to think about how you would do that, but I'm just going to show you how I'm going to do that. I'm going to put a mystery mass. I don't exactly know how much mass is on here. I kind of just picked up some random masses from my mass set and put them on here. And now I'm going to hang that here. And now I'm going to put this up here. This hanging stuff is 40 centimeters from the fulcrum. And I want to know what a graph would look like of the force in this force probe as a function of the distance from the center here. That's where we have to start in order to use the best fit to a straight line graph to find the amount of mass that's hanging and the force that it applies. All right, ready to go? I'm going to push down with the force probe, and I'm going to vary the distance that I push down at. And I'm going to record that in a data table here. I'll call that F2, the force that I pushed down with, and D2, the distance from the fulcrum that I push with. Now, this is not particularly exciting fare right now. I'm just going to get this data, and since you can see my spring scale, you'll be able to follow along with me as I get that. I'll tell you a story while I do the work. First, I need to zero this. 0. All right, I'll tell you a little story. You see, you might have noticed the first day that I had a 10-sided die. I really love randomization. I really love multiple dice, but you know what? I had never played Dungeons and Dragons before in my life, because that's what those dice are usually associated with. This is like 6.8 newtons thereabouts. And you're saying, wait a second, wasn't that 6.87 newtons? Wasn't it 7.0 newtons? It was a lot of things, but in AP Physics, I had that thing 10 centimeters from the fulcrum. In AP Physics, an obsession with precision is our enemy. We want to do quick and dirty labs where we can just push down and read. If we have to say, well, I don't know what that reading is, just pick one. Just pick one. 4.6 newtons. Boom, done. That was 15 centimeters. So I decided when the faculty here decided that they were going to play Dungeons and Dragons via Zoom, I said, why not? Let's try this. So 6 of us started a Dungeons and Dragons campaign. 3.3 newtons. And how precise are all these values? Well, you can see that the force probe is fluctuating between plus or minus, I don't know, about 0.2 of a newton is what I would say. What am I on, 25 centimeters? I'm going to push down right here. Why is the force probe fluctuating? Who cares? It's not because of human error, by the way. Don't ever, ever, ever say that phrase. 2.7 newtons. One more data point. Sound good? Or maybe 2 more. I don't know. Let's try a couple more. So I joined into this Dungeons and Dragons campaign, and Edna came with me. 30 centimeters. 30 centimeters gives me 2.3 newtons. 2.3 newtons. And Edna actually came onto the Zoom call the other day when we slayed a manticore. Somebody jumped on top of the manticore, climbed a building, jumped on top of this thing, and did it an enormous amount of damage. It was one of our dark elves. He's a French teacher, but I think he works better as a dark elf. I swear I had never done this before. I know I can give you encyclopedic detail about Star Trek Deep Space Nine, especially seasons 3 through 5. That's looks like 2.0 newtons there. And that's good enough. But I had never played Dungeons and Dragons. What can you tell me? All right, so we had our conversation. I know you guys have conversations when you're doing lab work in class. That's half the fun. And we're doing that here. The whole point was to get this data. Now, what are we going to do with this data? Got to use the dot cam now. We're going to graph this data. I know you can't see what's going on the board. I know you can't see that, but I can. You saw the data already. Feel free to follow along if you've got some graph paper at home. I want to do this graphing by hand. I do not want to do this graphing on a computer program, because on the AP exam, you'll be needing to graph by hand. I'm going to put D2 on the horizontal axis. I'm going to put F2, the force on the spring scale, the reading on the spring scale on the vertical axis with units. I'm looking behind me and I see that the force readings range from 2 to 7 newtons about, 6.8 newtons. So I can easily just go 1, 2, 3, 4, 5, 6, 7 newtons that way. I want the data to take up most of the page, more than half the page in each direction. I don't want to cram my data down here. That said, if it doesn't take up exactly the full page, that's fine. My distances ranged from 10 to 35 centimeters. So let's just go, I don't know, 5, 10, 15, 20, 40 centimeters. There we go. All right, now I'm going to plot each of these data points. 10 newtons, 6.8 centimeters. You go, Bertha can help out, or Edna can help out. 4.615, 4.6 newtons and 15 centimeters. We've got 20 centimeters and 3.3 newtons. We've got 25 centimeters and 2.7 newtons. We've got 30 centimeters and 2.3 newtons. And we've got 35 centimeters and 2.0 newtons. Look at that. We got a nice curve just like Edna's bottom. Notice what I'm not doing. I am not connecting my data point to point, and I'm not even drawing a, quote, best fit curve. While a best fit curve isn't totally wrong, we don't know anything about the data in between. Let's just let the data speak for itself. This data is obviously a curve, which makes sense because if we go back several slides, we found out that as we keep one torque constant and we move the force on the other torque toward the fulcrum, the force provided by that torque pulls up. That's what an inverse relationship is. Smaller distance, bigger force. So we expect a curvy graph like this. All right, but the problem that we're trying to solve asked for a linear graph. We need to linearize this graph. How are we going to possibly do that? We've got to do some analysis now. Let's write an equation that keep the torques constant. We know that F1 times the 40 centimeter distance from the fulcrum that F1 is. We'll call that D1, where D1 equals 40 centimeters. We know that that's equal to F2 D2. Let me solve for what's on the y-axis of my graph. That was F2. Everybody agree with that? Yeah, that's right. So now let's write the equation of a line. I like to use the technique that every time I'm asked to linearize a graph or something about what the meaning of the slope of a graph is, I like to write the equation for the line. I like to circle the vertical axis value because F2 is what we put. See that? We put F2 on the vertical. What was on the horizontal axis? Well, D2 was on the horizontal axis. I can't just circle X and D2 because D2 is in the denominator there. That's the whole reason why this graph wasn't straight. What can I circle here that would leave the slope to be F1, the constant force that was hanging? Well, I can circle D1 over D2. That means I want to make a new graph. I want to put F2 on the vertical, and I want to put D1 over D2 on the horizontal. When I do that, that will give me a straight line whose slope is F1. That's how to linearize a graph. Every time you are asked about the slope of a graph, I encourage you to write y equals mx plus b, circle the y, circle the x, and what's left is the slope of the line. Let's do this. I want to do this process. This is our original graph here. It's kind of useless now. I know that a lot of you are saying, why don't you just take the slope of that graph? You can't. That is a curve. We don't take the best fit slope of a curve. I've written a whole section of posts called Bad Graphs. If you want to go to my Jacob's Physics blogs, Jacob's Physics at blogspot.com, and you can Google bad graphs and you'll see a whole series. I've graded so many experimental problems. I've been on the readings since 1999. And somebody asked me, can you write up what the craziest graphs that you've ever seen are? And I said, sure. Now, I'm not actually giving information about individual students' responses. I'm just giving a general idea of what the mistakes are for people who are graphing. And that's one I've never put on there, but I realized, oh my gosh, I've seen that a million times. Don't take the slope of a curved graph. Here's what we're going to do. Oh, we're not going to do it on here. We're going to do it live. There we go. Yeah, you can see over here. I'm going to make a third column. It's going to be D1 over D2, where D1 is 40 centimeters. I'm going to plug into my calculator 40 centimeters divided by each of these numbers and make a third column. Fortunately, I already did that before class. I don't have to plug into my calculator now. What are the units of D1 over D2? Yeah, think about that. What am I doing? Hold on. 2.0, 1.6, 1.3, 1.1. Yep, I got it. There are no units because D2 and D1 are both measured in centimeters or meters or whatever distance you chose to use, and therefore the units cancel. These are just numbers, pure numbers that we can graph now. All right, let's go and graph the first column against the second column. Back to here. Once again, we've got F2 on the vertical axis in units of newtons. Same scale applies. On the horizontal axis, this time, we want D1 over D2 with no units. I think, let's see. Yeah, that goes 0 to 4. So let's make that 0.5, 1.0, 1.5, 2, 2.5. This is a skill that you will have to use on the AP exam sometimes, where you have to scale the graph yourself. We can't just use a computer program to do this. So I recommend that every time you do a laboratory exercise, you just decide to graph it by hand. So 4 goes with 6.8 newtons. 2.7 goes with 4.6 newtons. 2.0 goes with 3.3 newtons. 1.6 goes with 2.7 newtons. 1.3 goes with 2.3 newtons. And 1.1 goes with 2.0 newtons. There we go. You like that? Yeah, Edna likes that. Everybody say hi to Edna. Everybody likes Edna's bow. All right. So what do we do with this? We take a best fit line. Now, you're going to say, wait, couldn't you draw a best fit line a little lower, a little higher? Of course I could. A best fit line is not a magic principle that there is only one divinely obtained best fit line. Each of these points I'm going to show you here is plus or minus about 0.2 newtons. If you remember, the scale was fluctuating by at least 0.2 newtons every time we tried to take a point. So what this really is like that. I'm drawing air bars. Now, those of you who are in AP stats or in another math class might be screaming at me now. You got to do that more rigorously. Not really. An obsession with precision is the enemy in AP Physics 1. Point is, I can draw a best fit anywhere within there. I'm going to choose to draw the best fit like that. Now I take the slope of the best fit. To take the slope of the best fit, I choose 2 points that are not data points, that are far separated from one another, and I simply write out rise over run. The rise here is 6 minus 1 is 5 newtons. The run is 3.5 minus 0.5. No units on that. Which is, to 2 digits, 5 divided by 1.3. Looks like 3.8 units of, slopes have units of the y divided by the units of the x, which is just 3.8 newtons. If I wanted to get an uncertainty on that in a non-rigorous way, I might draw a steeper best fit line and a shallower best fit line and take those slopes. I'll bet you any money you find out that the uncertainty in that would be plus or minus about 0.2 newtons, because that was what the uncertainty in the reading of the force probe was. But that's as much rigor as we need. We don't need to go into long, detailed mathematical uncertainty analysis. Just an understanding that each point on a graph has a plus or minus value that can be represented either by the size of the dot or the air bars, and that a best fit line has an uncertainty that you can kind of guesstimate. That's good enough. So I told you that there were that the hanging weight was I'm sorry, not 3.8 newtons. What am I talking about? I'm sure the Twitter feed is going nuts now. 5 divided by 3 is not 3.8. Thanks. It's 1.7. 1.7 newtons is what I'm predicting, right? So let's see. I should get 1.7 plus or minus 0.2 newtons, which means I should get 170 plus or minus 20 grams. Shall we check? There was an old game show called The Joker's Wild, where this is in the 70s and 80s, where at the end, whoever won money would get the money counted out into his or her hand, and the whole audience would scream, 50, 100, 120, 130, 140. Whole audience is screaming this, not just me. 100, I've lost track now, 120, 30, 40, 50, 70, 175 grams. Physics works. Isn't that amazing? All right. What's the moral of this story? There was a lot that just happened in that in that little segment. I'm going to go talk about it in just a moment here. All right. What did we think about? An AP exam that is posed in a laboratory setting will start with, often, how would you measure something? You have to tell me, what are you going to measure and how are you going to measure it? Describe a procedure. To do that, you need to use no more than 3 sentences. Shall I do that for you? Describe a procedure to measure the force as a function of the distance from the fulcrum. Well, I would say, with that diagram that I already made, I would say, press down on the meter stick with a force probe. I've told you what I'm going to measure. F2 with a force probe. The distance from the fulcrum, which I called D2, can be read from the meter stick. And look what I just did. I didn't put it there. That's good enough. What did you measure and how did you measure it? If you want to, you can then say, we varied the distance D2. That's fine too. That's all we need. We don't need a 12-step procedure. If you're starting your lab procedures by saying, we came into lab today and found our partner, that's wrong. Assume an audience for your experimental question that is well-versed in physics. Assume a senior undergraduate, because they understand that you recorded your data carefully. You don't have to tell them about that. They understand that you came into lab and gathered your equipment and designed a thought of how you're going to do the experiment. Don't tell me about that. You don't have time. Just write your procedure very briefly. What did you measure and what equipment did you measure it with? A diagram is helpful. I showed you that diagram before. That's useful, because then we can see that you know what equipment you're using. We do need to be able to tell that when you say use a force probe to measure the force at various distances from a fulcrum, we need to know that you're not using the force probe like a radar gun. Doesn't work that way. We need to know that you know how to use the equipment you're using. But what I wrote there is fully sufficient. You might be asked to use the best fit to a linear graph, in which case you need to know how to linearize a graph. That's where you write y equals mx plus b, circle the y, circle the x, and what's left is the slope. Find the physical meaning of the slope that way. Take the slope of a best fit by drawing the best fit with a ruler, by taking the rise over run, and then putting units on your slope. And that is basically a full-on 12-point experimental design question. All right. I'm going to give you another problem, but first, as I promised, I am going to go to @JacobsPhysics, and I'm going to go to the notifications, and I'm going to start answering questions. Where do you get D1 and D2 from? Did you just choose random values that weren't a part of the data? Not exactly. If you go back to, yeah, you can go back to the table right here. We said in the original problem that D1, the distance of the mystery mass from the fulcrum, was fixed at 40 centimeters. That's why I divided 40 centimeters by each of these values right here when I did my linearization. D1 was fixed. D2, how did I decide what variable or what values to use? I just said, all right, 10 centimeters looks good, 15 centimeters. Did I have to go by 5 centimeter intervals? No, it doesn't matter. I could have easily done 7 centimeters. If I didn't like the way that graph looked, instead of retaking a data point, I would have just gone, let's try one that's pretty close. Let's try 14 centimeters and see how that works. You can take as much data or as little data as you want in order to fill in the parameter space. What else do we got? Who is Edna? This is Edna. She's my pet hippopotamus. Say hi to Edna. Yeah, and somebody responded to that. Let's get another one here. And do not, somebody said, that's a jar of pickles. No, Edna is not a pickle. Edna is a hippopotamus. She has a nice little bow that my wife put on there for her. Yes, let's see here. Why did you say that we shouldn't ever say fluctuation due to human error? That comes from the old Shakespeare. I think it's Shakespeare. I'm not an English teacher. To err is human, to forgive divine. That's not what physics is about. There's no such thing as human error. There is an uncertainty in the scale reading. You say, well, couldn't it be because I was pushing harder or softer? Well, that's what a scale reading does. That's not human error. That is uncertainty in the scale reading and in the actual measurement itself. How is that taken into account in the actual experiment? It's taken into account by looking at these things. And it's taken account by looking at these error bars and making your best fit line go the way it was. I don't know that I was on this when I showed you Edna. This is Edna. Say hi to Edna. She's got a nice little bow in her hair. She's a hippopotamus. What other questions do we have here? Oh, we have somebody who plays as a rogue. I learned about rogues, and a shout out to all the dark elves. Consider let's see, what do we got here? On the question from the beginning of the live stream, why is it that the fulcrum must be established at T1? That's a really good question. There's no point given, so you could put the fulcrum at MG. She's referring back to the original question we asked today, which I will put up on the screen if I can find it, because once I use these slides, they just go way away from me. Here it is. All right, I found that. The question is, why did I put the fulcrum here? Well, because I was asked about T2 and MG was pulling down, making a opposite torque to T2. You can choose the fulcrum in this case any place you want, but by choosing the fulcrum at T1, that allowed me to equate the torques provided by MG and T2. If I had put the fulcrum at MG, then I would have had to know something about T1 in order to know about T2, and I didn't know that. When you have something that has a clear fulcrum, as in the experiment that I did in class today, then, well, you have to use the fulcrum that's given. In this problem, I pivoted the meter stick at the halfway mark. But if I'm just holding up by 2 positions, I can use any fulcrum I want to establish the value of the forces in that case. Great question. Let's move on to, I've got about 6 minutes left, so I will put a couple more here. And let's see, it's at Jacobs Physics if you want to communicate here. And I'm not seeing it. There we go. Okay. Let's go to the very beginning. Can I re-explain how to linearize the graph? I'll show one more time the linearization process in general, and then I will move on to tonight's problem. Go into the dot cam, and the dot cam is on. All right. So I started with a recognition that we have a constant value of 40 centimeters for D1, and I equated the torques. This is the equation that describes the situation. I solved that equation for the vertical axis of my graph. I then wrote y equals mx plus b. That's the equation for a line, the equation you learned many, many years ago. Circle the y. I want to circle the slope with F1 because F1 was what I was trying to find. So by circling the slope with F1, whatever's left, I have to put on the x-axis. So I had to put not D2, but D1 over T2 on the x-axis. And sure enough, when I graphed F2 on the vertical and D1 over D2 on the horizontal, that's what I got, a straight line graph. That, folks, is linearization. All right. If you have further questions, if you go to @JacobsPhysics, I will try to answer them for the next couple of days. There's also, if you want to go to Josh Beck's Twitter account, it's @Mr. JB Physics. Try that. I've linked him on my Twitter. You can take a look at that. You can ask questions to him. He did a great job yesterday, and I appreciate it. But he's not coming back on Monday. He's coming back on Tuesday. I got you on Monday. And on Monday, we are going to be discussing Newton's second law for rotation. Here is the problem we're going to be discussing. And I will, in fact, try to post this on my Twitter feed so you can see it. We've got a disk rotating counterclockwise as shown with an angular speed. And then we exert these two forces. We want to know which of the following could be the angular velocity of the disk as a function of time. There's your four options. Don't answer first. If you're going to justify this answer, it's not justified like you would on a news program like, I think it's B. No, John, I think it's C. C. That's not how we do it. What we do is we write the facts of physics that apply, and then we write a connection from the facts of physics to the actual answer. And I will start there on Monday morning. Two more things before I go. Device and internet access. Obviously, everybody who's watching me right now has a device with internet access. I gotcha. But we know that not everybody has access. So not if you need mobile tools or connectivity, because you have them. If you know somebody who does, reach the College Board at this link. And from that link, you can fill in a survey that explains the issue. I'd encourage you all to spread the word to your friends. So thanks for watching. We're on every day at noon Eastern. And on Monday, Edna and I will discuss Newton's second law for rotation. I'm going to have a big twirly thing right where this is. And I'm really looking forward to seeing you there. Take care, folks. This was a lot of fun.